So, hello everyone. I'm Alexandre Brun from Noveltis, and so today I'm going to present to you a Jupyter Notebook tutorial on this Mediterranean workshop. So for this notebook, I've chosen the topic salinity in the Mediterranean Sea because the Mediterranean Sea has its own particular dynamics in terms of salinity. As it is a quite isolated space here away from the open ocean. So you will see that it does have an influence on the salinity levels because it tends to has a higher salinity than the open ocean, for instance. And it also has particular dynamics because on the western side, we have a clear influx from the Atlantic Ocean that well drives the salinity dynamics in this area. And on the contrary, the eastern part is more isolated. So this is why salinity is quite crucial parameter to monitor in this region. And we will see in detail what are the potential factors and drivers that I've mentioned, and we'll try to analyze them in detail in this notebook using data from the Copernicus Marine Service. So yes, here's a brief overview of the area. So we'll be working with Python, with some of the most common libraries that you encounter in Python. You're probably already familiar with some of them if you work with Python before. So we'll be using NumPy, which is a fundamental package for scientific computing. Xarray is a standard Python library to compute netcdf files, which is the standard format for scientific data, um, which is, well, the format in which most of the Copernicus Marine Service data comes. And we'll use Matplotlib and Cartopy to draw the different maps and graphs that we'll generate in this notebook. These libraries are pre-installed in the Copernicus Marine Python kernel in the Copernicus Marine Service Jupyter Lab. So make sure you have it activated if you're working on the Copernicus Marine Service Jupyter Hub. And with this cell, we can import all those libraries at once. So we're almost ready to go. Now I'm going to quickly do an overview on the data products that we are using in this training. So we are using the Mediterranean Sea physics tree analysis. So it's a combination from model data and observation that are assimilated within the model to improve its accuracy. There is a dedicated page that you can visit on the Copernicus Marine Service webpage, which will give you more in-depth knowledge of the product. You have access to the user manual and quality information document here. So this gives you additional information on all the variables, how the product was built, etc. Some references, and on the bottom of the page, you have some more information, practical information on the product, such as the variables that are available, the resolution, the temporal coverage, etc. So here's a summary of the information that will be the most valuable to us. So we'll be retrieving the salinity variable, so it's called SO, the seawater temperature variable, and the current components, so the horizontal and the vertical components. We have here spatial resolution, and also an important attribute is the depth level. So you can see that we have 141 depth levels in this dataset. And finally, we'll have daily and monthly data available. So we'll try to work with both of those temporal resolutions, depending on the section here that we'll analyze. And we have a temporal coverage going from 1987 to 2025. So in our case, we'll just use data on a single year. This will be enough for us in this training. And finally, you've already had previously presentation on how to use the Copernicus toolbox to retrieve data. So this is what we are using here to retrieve the data in this Jupyter notebook. So we are using Copernicus toolbox with the associated Python API. So same thing, if you make sure that you're using the Copernicus Marine kernel, because that way you'll have access to the Copernicus Marine library, Python library. Then this will allow you to enter your credentials within the notebook. And once this is done, you will be able to download the data as many times as you need. In this notebook, we're using the subset function that is well detailed in the articles that were presented by Anais in the previous presentation. So here's a quick practical example of how to download the data for this notebook. So here we can see that I'm retrieving the salinity variable from this dataset. So to find the identifier of the dataset, go back to the Copernicus Marine Service page of the product, go to the Data Access tab, and find the variable that you need. So in our case, we want the salinity. If I remember correctly, yes, we want the monthly values. So this is the ID that you need to copy and paste in your Jupyter notebook here. And then to find the exact name of the variable, click on Form. And here you will see that the seawater salinity is called SO. Then make sure that the date, start and end date times are within the temporal coverage of the product. So here 2022, we seen before that it went to up to 2025, so it's perfectly good. We're going to download the entire year. And here we are retrieving the depth levels. So we're going to this is the closest layer to the surface, and we're going up to 5,000 meters. This is quite an arbitrary choice, but it covers almost all the depth levels available in the data. So I've already pre-downloaded everything, but you can see that it is quite fast to download using the Copernicus toolbox. So you'll be ready to go right away. You can see here, seconds ago, the product was added to the to my data library. All right. So now we are ready to open the product using Xarray and explore it a little bit. So here is the Salinity product that I have just downloaded. And when you use Xarray in Jupyter, this is the output that you have when you open it. So you can take a look at the dimensions that are available. So as expected, we have 4 dimensions. We have the well, the geographic latitude and longitudes. We have 12 time steps because we have monthly data over a single year, so 12 months. This is also consistent. We can see here, click on this icon, we can look at a sample of the data that is available. So here for the time variable, we can see that we have our 12 values going from January to December 2022. Same thing here, can have some, take a look at a few values here, but we have more of them, so we can't look at all of them at once. And we have our depth levels. So it is here. We can also have a quick sample here. So it's 1 meter below the surface to almost 5,000 meters below the surface that we have available as layers. And finally, this is our salinity variable. So if you click on this icon here, you can display the detailed metadata of the variable. So it's indeed the seawater salinity. Here are the maximum and minimum valid values, and here the unit, which is basically the standard salinity unit, which can be expressed as grams per kilogram of water. And here's some more global metadata on the product with references, detailed titles, and other details such as the CF convention that is followed by the netctf files, etc. So in this first quick overview, we're going to simply look at the surface salinity at surface level, so at the first depth layer. So to do this, we can use the cell method to subset the product along certain dimensions. So here we want to retrieve the nearest level to the surface. So we're just going to use depth equal to 0 and using the nearest method. And then we use a squeeze function to make sure that the depth layer is erased and we don't have a remaining fourth dimension with only one level, which could cause errors in later processing. So that we can see that thanks to this operation, we have retrieved a single depth level here, and it's not expressed in the dimensions anymore. So now we have indeed surface salinity data. Now in the next section, I'm going to show you a simple map of the surface salinity over the entire year of 2022. So using this cell, I'm just going to draw a bounding box over the Mediterranean. And here I'm computing the average salinity over the entire year of 2022. So using the mean function over the dimension time. So you can see that now that I've averaged over the time dimension has disappeared from the dataset, and we only have latitude and longitude remaining. So this is all we need to draw a map. So here's a quick setup to draw the basics of the maps, like the coastlines, zoom in on the box that I've defined, and draw the geographic grid lines. And now using the P color, I can color the Mediterranean according to the salinity values along the latitude and longitude dimensions. Takes some time to draw. So here's a quick overview of the average salinity in 2022. So as we could expect, there is the influx here from the Atlantic Ocean that caused the salinity to be a little bit lower in this area. And on the contrary, we have higher salinity in the more isolated zone here in the Eastern Mediterranean. So this is what I had mentioned in the introduction. So this is quite consistent with the hypothesis. So we'll try to study this regional dynamic in more detail in the next section. So now we're going to do a very simple east to west comparison. Basically, plotting the western and eastern distributions of monthly salinity in two separate box plots. So to do that, we can subset the data set on the western side and on the eastern side. So here we're going to compute two separate data sets. So based on longitudes here, we're going to plot this part and this part separately. And now we'll draw box plots of the monthly distributions of the two of the average values over the western and the eastern parts. And we can see that the two distributions don't even have an overlap here. So this shows that the Eastern Mediterranean has a significantly higher salinity over the entire year of 2022, regardless of the season. So yes, this difference is quite stable over the year. So now in this next section, we're going to look at that in more detail and see the evolution with time over the year 2022 to see if there is a changing pattern depending on the season. So basically, I'm going to draw the same map, but this time not over the yearly average, but I'm going to draw this map for every month of the year and animate and gather these images into an animation. So this is what is done in this cell. So I'm not going to do it now because it takes some time to draw the 12 different plots. So I have pre-done it in this. Oops, sorry, here. I've prepared the 12 plots here. And they are gathered in a single animated GIF image, which looks like this once we animate it. We can see the month here. And we can see that the spatial pattern of the salinity remains stable along the year. The noticeable change that we can notice is a clear increase in salinity here during the summer, which suggests that well, this salinity increase is likely due to the intensified evaporation because of the high temperatures in summer. And we also have a strong local decrease here in salinity during the summer. And I would say like spring or early summer, which is most likely due to well, freshwater influx here, perhaps from the melting of potential snow in this area. So we can also see the influx here from the Atlantic Ocean, and the next section will be dedicated to this interface here with the in the Gibraltar Strait. So for this more detailed analysis, I'm also going to retrieve currents data to see the dynamics at this interface. So same thing as before, retrieve the find the currents dataset in the DK page and retrieve the two components of the currents. So if I open it, we can see we have the same dimensions. Note that in this time, I'm only retrieving data very close to the Gibraltar Strait. Same thing here. And this time, what I want to do in this section is to find the vertical profile of salinity and currents to see how the water is exchanged between the Atlantic Ocean and the Gibraltar and the Mediterranean at this interface area. So this is why I'm averaging the data over the time, longitude, and latitude to have only a vertical profile along the depth dimension here. So I'm going to subset the data over this area on the Gibraltar Strait and plot the currents and the salinity on the vertical level, on the vertical axis of the depth. And this is what we. I'm going to zoom out to have the entire graph visible. So on the left is the velocity of the water profile, so going from west to east. And here is the salinity. So here the horizontal axis is salinity, so high salinity and low salinity on the left. And what we can see is that above the above 100 meters below surface level, we have a clear flux of water going from the Atlantic towards the Mediterranean. And we can see that this water has quite lower salinity here. So this is exactly the influx of water from the Atlantic Ocean that we had mentioned in the introduction. And on the contrary, below 100 meters depth, we have on the contrary water going from the Mediterranean to the Atlantic Ocean. And this time, this is high salinity water that goes out of the Mediterranean. So this is quite an interesting dynamics, and this clearly explains why we have much lower salinities in the Western Mediterranean Sea, with an influx of low salinity water and an outflux of high salinity water. Next, so we have these dynamics in the Gibraltar Strait, and now we can look at how it mixes with the rest of the Mediterranean Sea by plotting the vertical profile along an entire transect here. So if you do this notebook at home, you can get creative on how you draw this transect. So here is what we've done for this notebook, but you can change it and try other curves. Takes some time to compute here. Okay. So same as before, we've plotted the vertical profiles of the salinity. So basically, it is this curve, but replicated several times along this transect. And we can see that we have still here near the Gibraltar Strait this clear separation between a low salinity layer and a high salinity layer. But then as we go further into the Mediterranean, we can see that it mixes with the water. And here in the middle of the Western Mediterranean Sea, we can see that now the transition between the surface and the deeper levels is very smooth. And finally, in this final section, we are going to look at another potential driver for salinity in the Mediterranean, which is temperature. So same thing as before, using the same product. This time we will retrieve daily salinity data. Daily because we want to compute correlations over the year 2022, but we could have done this over several years. This is just an arbitrary choice. But we need to retrieve daily temperature to have as many data samples as possible to have a stronger correlation. And well, 12 monthly values wouldn't be enough. So retrieving the daily salinity temperature, retrieving the daily temperature, daily salinity values and daily temperature values. This time we will only be looking at the surface, so we are retrieving a very shallow depth layers. Here we open the datasets, and as those two datasets come from the same product, they have exactly the same dimensions, shapes, etc. So it's very easy using X-ray to calculate the correlations between those two. We don't have any interpolation work to do. So we can use a built-in correlation function of X-ray along the time dimension, of course. And now we are able to draw the correlation map here. Also takes some time to draw. And yeah, this is a quite telling map, especially for the eastern part here, where the temperature is very strongly correlated to the salinity level of the water. So this is consistent with the hypothesis that evaporation is the main driver of salinity in this area, because here it clearly tells that the higher the temperature, the higher the salinity. We can see this western part that we have sometimes positive correlation, sometimes negative. So this shows that there are some external factors outside of temperature that also influence salinity in this area. Those are more complex patterns. And we also have here in the Northern Asian Sea quite strong negative correlation here on the contrary. So this shows that we have quite different processes at play here that explain the levels of salinity of the water. Perhaps influx from the Black Sea here that could have a strong influence, and also French water influx from local rivers. So this is something that could be further analyzed using more data. So we're reaching the end of this notebook. So if you're doing this on your own, we have prepared some exercises if you want to go further in the analysis and play a little more with the data. I'll go quickly over the beginner levels, but well, we can draw the different math that we've shown on different dates, for instance. And yes, as I said before, you can get creative with the transects that we are using here to compute the vertical profiles of salinity. You can even draw transects going further here in the Mediterranean, and especially in the center area where the local dynamics tend to visibly change here. So this could be interesting to see how the layers interact with each other in this area. And yeah, and also don't hesitate to try to compute correlation with other variables available in the data sets of the Mediterranean reanalysis. This could yield some also interesting results. All right, so I'm finished for this notebook. If you have any question, don't hesitate. Don't hesitate. Thank you for your intention.
Thanks a lot for the presentation, Alexandre. We have a few kudos on the chat for the notebook, and yeah, a few questions also. So we start with these. The first one being, could you have compared both vertical profiles from the Atlantic and the Mediterranean Sea, or the resolutions were different?
Not too sure exactly what you mean by that. Do you think I could have compared something, some data further from this on this side of the Atlantic, maybe?
I would say it's about the salinity profile, because I think you did I think it was when you showed the transect of salinity in the
Yes.
Mediterranean. So I think
Oh,
it's,
okay.
yeah.
Yes, it would have been interesting to prolong this transect towards the west. It's just that the Copernicus Marine Service product of on the Mediterranean Sea stops at this boundary here, if I'm correct. So yes, we don't have any data on this product outside of the Mediterranean, so I should have combined another product to have the complete transition here. But yeah,
Okay.
that's some further work that can be done to have a better view of the layered interaction. But yes, you would have to do some I don't know, adaptation work to do to efficiently join the two products, probably.
Yeah. Okay. Okay. Thanks. But yeah, the Mediterranean product effectively end at the Gibraltar Strait, so it would have been another one. Oh, okay. The next one, if we look the correlation between salinity and temperature over several years, do you advise to keep the daily data, or can we use data with less temporal resolution, mainly for calculation of cost?
Yes, with several years available, I think I would probably also switch back to monthly data. What matters to me in this case is to have a sufficient number of samples to have a reliable correlation result. So yes, I think for the same concern also to be able to compute that more easily because daily data over several years quickly becomes difficult to manage. Yeah.
For the advice. Okay, so this one I can answer. Where can I download the Python script you use in the Jupyter Notebook? So on the chat where you see the live stream, we send you the link to the page where you can download the Jupyter Notebook. You will also see it on the top bar of the event page. So you just click on the Jupyter Notebook and you will find all of the Python script and also the full video demonstration of the tutorial, because today was a quick summary mainly. But yeah, that's it. You can download it whenever you want. And it's also available on the Jupyter Hub of Copernicus Marine. This one, yeah, I think it's more a comment. The Mediterranean Sea seems to be more salty than some other seas that could be warmer. Is it because it's closed?
Yes, and with what we've seen, especially in the eastern area, which has a very little influence from the Atlantic, on the open ocean influx here. So yeah, this is an area where it doesn't have many interaction with fresher water. So with also the strong temperatures here, where you have evaporation as the main driver, which causes a high salinity. Yeah.
Okay, thanks. Okay, so this, well, I can answer this one. So it's still about the tutorials and articles. So everything is always available on the website. So yeah, don't hesitate to check and you can look with the search bar with keywords to find the articles you need for the tutorials or the Copernicus Marine Toolbox. We also have a few questions about the datasets you used. I don't know if you know the answer to this one. How many data points are there at Gibraltar? Is the water flow only in one direction, or it could be flowing in different directions at northern and southern parts of Gibraltar? Do you remember what was the resolution of the dataset you used?
I can show it. So here I had downloaded for this section a smaller dataset, very restricted to the Gibraltar Strait area. I haven't plotted it exactly, so I don't exactly remember how much the resolution was. I can take a quick look, but hopefully it I won't have an error and embarrass myself right right now. Um, yeah, I'll try to go quickly with this. Well, let's sorry, I think it will take too much time to yeah.
Yeah, but I think it
But
should have
you have
a
the number of data points here in the 2D dimensions. And from the current, so yes, I've only looked at the eastward component because I assume that in this interface, the inflow would be mostly in the east to west direction. So I've only looked at the eastward components of the current component of the current. But yeah, you could get some more complex patterns if you look very closely. But I've just assumed that the main interesting direction would be east to west in this particular case, which is convenient
yeah.
because Gibraltar side is quite horizontal.
Yeah, but yeah, on the dataset you have the four direction. You have eastward, westward, and you also have the southward and northward
Yes, you
direction.
could
So
totally draw
yeah,
a complete vector field here for the currents and see the direction details. But yes, for simplicity in the sake of this tutorial, I haven't done this.
yeah. Okay, thanks. So we still have a few questions. So thanks for the interesting tutorial. Why does the transitioning in salinity and velocity happen at 100 meters below the surface?
Well, I wouldn't be able to explain exactly why this happened at this particular level. Um, I think it's a quite common phenomenon in this particular area, but why 100 meters? I wouldn't be able to exactly tell you why, actually.
Yeah, I guess it's just the point where the salinity change in the value. Yeah. Um, uh, okay, so another one. So when you import the data of the Gibraltar Strait, when you recalling the data from the website or from the previously downloaded dataset. So you used one dataset, if I'm not mistaken. So
Yes.
yeah, it's still the
Uh,
same.
yes, I sent several data requests to the same dataset. So as mentioned here for the Gibraltar Strait focus, I sent a new request towards for the currents, but for the yes, it's only always from the same dataset. So
Mm.
here I'm sending a new request for the currents, but I think that for the salinity, I just reused the product downloaded in the previous sections, if I'm correct. So here it's the currents. I can't find the yes. Gibraltar. Yes, I'm using the first salinity dataset that I've downloaded in the beginning of the tutorial.
Yeah.
I just subset it to the Gibraltar Strait, so within this box here.
Okay, thanks. Now we're sure. So we have another two questions about the correlation between salinity and temperature. So the first one being the more general one, what other factors lead to completely negative correlation between the temperature and salinity? And the other one being, could you explain why salinity and temperature have varying correlations? Physical oceanography class.
Usually it's because you have some other phenomenon that completely dominates in a very local area. I assume you're talking about this particular part here. So this would definitely deserve some further research. The hypothesis here were the influx from the Black Sea and potential fresh water here from the continents, which is what we had assumed in this area. In those other areas where we also have a lot of negative correlations, same thing. We have several patterns that we can't observe with our limited data set that we have here. We only had temperature data. But definitely here we know that we have the freshwater influx from the Atlantic that also has an influence. So when you have several factors kind of influencing the salinity, you need to compute correlation for all of them and try to assess what are the dominant ones. Here it means that temperature is not one of them.
Okay. Okay, thanks a lot. So yeah, that was it for the question about the tutorial. Yeah, thanks again for the presentation, and yeah, I think people quite enjoyed this tutorial.